Hello, my name is Dewitt Godfrey, the Peter L. and Maria T. Kellner Endowed Chair in Arts, Creativity, and Innovation at Colgate University. We would like to thank my institution and my partners at AKT II for their support and the IASS conference organizers who no doubt wish we could all be together in Surrey. Since 2012, our team of myself and the computational designers and engineers at P.art of AKT II have collaborated in the development of new digital design methods, modeling, simulation, and fabrication tools, expanding the material and structural complexity of my sculptural systems. Prior to 2012, my sculptures were informal and improvisational arrangements of thin-gauge steel cylinders where the shape of the individual elements resulted from and were determined by gravity, adjacency, size, scale, and material behavior. Our proposal for IASS 2021 has its origin in these sculptural works, a series of manually designed and assembled structures composed of both flexible materials and connections that allow these dynamic systems to exhibit a range of behaviors. These structures performed in a crude fashion like natural living organisms. They were only semi-predictable and, much like a plant, could vary in form depending on the environment in which they were sited. As in nature, these variations were not indiscriminate and could only take on forms prescribed by the genetic or structural code inherent in their material and construction. Here are before and after images of Driggs following a heavy snowfall at the Black and White Gallery in Brooklyn, New York in 2002. A direct iterative process informed these works, exploring ways to preserve or alter the system's behavior through simple modifications, such as using a single thickness of material but varying the cylinder diameter, multiplying the number of cylinders in the system, or varying the material thickness in individual cylinders. The process was intuitive with little formal engineering, and the forms were limited to linear, fence, or wall-like arrangements. As the scale and complexity of these works grew, it became clear that there was a need for more control and understanding to undertake these installations safely and to discover the next step in the evolution of the work. In 2012, with Daniel Bosia of AKT II and mathematicians Thomas Tucker of Colgate University and Tomasz Pizanski of the University of Ljubljana, we received a grant from Colgate University's Picker Interdisciplinary Science Institute to explore mathematical methodologies for art and design. We worked to develop methods to generate ideas and forms comprised of a set of digital tools and physical processes for form finding. Over a 3-year period, our research culminated in the design, fabrication, and installation of Odin on the Colgate campus. The methods created during our research project built on the physical ways form emerged in the earlier work. These newly developed digital tools made it possible to break away from linear arrangements, allowing us to pack conical sections on complex surfaces. What distinguishes our work from that created through more fully automated processes is digital invention and precision coupled with material imagination and expressiveness, both areas of expertise meeting in a space of semi-predictability where cutting-edge digital forms are resolutely handmade. Across all of these projects, a series of themes have emerged: material behavior, spatial connectivity and packing, and the relationship between component and assembly. As our understanding of the structural behaviors that govern these systems has grown, the complexity and scale of subsequent sculptures has been able to increase, and new ideas have been introduced that morph and reformulate these relationships. For the second half of our presentation, Joel Hilmersson will provide more detail on the evolution of the computational methodology and introduce the Geldeford Riband. Pictured here is Eastgate under construction, an example of our new ribbon typology. Thank you.
During our collaborations, each project has, with its specific restraints and intentions, challenged us to refine a set of computational processes. The project that started the series of 3D sculptures was Odin back in 2015. Here, the geometric description was done through a spring system in the grasshopper plugin Kangaroo. Each node in the system was placed on a surface, given a radius, and allowed to attract and repel nearby nodes until equilibrium was found. These points, with their respective radius, was then used for the generation of the physical hoops. A problem that presented itself during the design of Odin was that the packing was not perfectly cotangent. To resolve this, for a subsequent sculpture, additional steps were introduced in the form of a VORONOI cell division, followed by a smoothing process. This was set up to ensure coplanarity at the connection points. The algorithm used for Odin had been successful, but in later projects it lacked flexibility as the artist desired a finer control. Therefore, during the Inspire project, the kangaroo implementation was substituted with a custom process. This process has been slowly expanded upon and now allows, for example, for circles to dynamically adjust their radius and for the artist to intuitively add additional ones both while the process is running. This aims to replicate the process of the earlier, more informal cylindrical sculptures in a digital context. A more recent problem that have emerged is how to deal with complex boundary conditions, for example in the ongoing Portland sculpture, which interacts with external geometric constraints. Here, the control surface is mapped into 2D space for the packing, and then remapped back into 3D space for the physical hoop generation. The proposal for the IASS pavilion continues the development of these projects by extending them with 2 new directions. The first direction is how to link the form and behavior on a global scale in terms of structural performance. The base form has an inherent stress distribution which depends on geometric features such as apertures. This can be found through an initial FE analysis using the surface as a shell. By representing the distribution as a grayscale gradient, it can be used in the circle packing process. The circles in the packing then readjust locally with an awareness of the relation to the global behavior. Regions with higher stress get a higher density of material as the circles in these areas reduce their radius and pack tighter. This creates an interconnection between global features and the local components through the overall behavior. Using different base geometries with different stress, a wide range of similar yet distinct options could be tried. The second new direction is introduction of a new typology in the form of an elastic, continuous ribbon made from polypropylene. Ribbon geometries are generated from the cell division by combining sets of hoops into topological clusters. The steel hoops roll into an explicit form, but there is an inescapable elastic nature to the components, and these topologies can be understood in relation to their self-forming behavior. To capture this behavior, simulation models using the engineering extension for the Kangaroo plugin were set up. The outcome of this simple model was compared to a physical prototype with good correspondence. The final pavilion design can be seen here, which features a total of 42 ribbons. To use lightweight, flexible, and resilient polypropylene for the first time in a Godfrey sculpture will help create a responsive structure full of light and space.